His video is on thermochemical equations. It's page 3 of your notes. Term that's not on there would be this term. I would add to your notes here. It's called enthalpy. This is probably the major thing for this chapter. You will see thermochemistry twice this year, a little bit early on, a little bit later in the year, and it kind of goes through everything that we do the rest of the year, just a little bit. So enthalpy, the symbol is H. Delta H means change in enthalpy, which we're always worried about in a chemical reaction. It's just the heat change in a chemical reaction that's at constant pressure. Constant pressure part's not that important, but so enthalpy, again, delta H is the heat change in a reaction. So the H kind of stands for heat. It's really not what it is, but enthalpy change is that. So the enthalpy change in a reaction would be, if you want to know the delta H, or the heat change in a reaction, we take the product's heat energy, usually in kilojoules, minus the reactant's heat energy, also in kilojoules. Okay, and just like it's not really much different than Q when we're doing Q equals mc delta T, which is heat flow. So just like a positive Q is endothermic, a positive delta H means there's an increase in energy, means it is endothermic. So a positive delta H is endothermic. A negative delta H, negative enthalpy change, is exothermic. And a lot of times we'll deal with some energy diagrams for a reaction. So let's say we have reaction A plus B forms reactant C plus D. So there's our generic chemical reaction. There'll be a little energy diagram. So this would be like our kilojoules of energy as a reaction goes. Let's say that our reactants have this many kilojoules energy. Let's say that's 400. The reaction goes. So these are our reactants. This is our A and our B, our reactants. That's how much energy they have. So they have 400 kilojoules energy. This little hump right here we'll talk about at some point in time. That's called the activation energy of the reaction. That could be really big. It's the energy it takes to start a reaction. And then these would be our products down here, C plus D. So in this case, reactants have lots of energy, products not as much. It's an exothermic reaction. That difference change. So that change, if I draw a little dashed line right here, the change in energy there to there. So let's say this is 400 kilojoules. Let's say that this is 100 kilojoules. That change would be our delta H. In this case, our delta H, since it's going down from 400 kilojoules for our reactants to 100 kilojoules energy for our products, that delta H should be a negative 100 kilojoules. We've lost that much. That means that much heat went into the surroundings. 100 kilojoules of heat went into the surroundings, left the reaction. So you would feel heat being given off by that reaction. Again, that would be a negative delta H, or a negative enthalpy change. Reactant energy, products energy. If our products were low, if our reactants to our products, if there's an increase in energy, then that's a positive delta H, an increase in enthalpy. So that'd be a positive kilojoules. All right, so we'll talk more about energy diagrams, but that's kind of the basis of those. All right, just going to do these couple problems right here. That's it. So this is a thermochemical equation that usually tells you the delta H. There is a way to determine delta H from a chart that we'll have to do quite a bit. This reaction is giving you the delta H. So you just say, okay, here's our reaction. Here is our enthalpy change. So what that means is it's exothermic. As this reaction goes, heat is being given off to the surroundings. This is actually the burning of vanadium. It's combusting. So you would feel a lot of heat being given off as this reaction goes. So if we were drawing our energy diagram, again, our kilojoules of energy, the vanadium and the oxygen have lots of energy. There's that little hump we'll talk about again later. There's our vanadium and our oxygen, those are reactants. Our product is V2O5, has way less energy. And the difference in these two, the difference from this line to this line, that difference would be our delta H, which in this case is a negative 1579 point whatever kilojoules. So there's a lot of heat being given off, a lot of kilojoules of energy being given off. Notice that is in kilojoules per mole. So if you look at this reaction, you probably see something different than normal. 2, we have a 5 halves, okay? The reason there is a 5 halves, there'll be some fractions in this, fractional moles. So that means for every 2 moles of vanadium, there's 2.5 moles of oxygen. They were trying to keep it per mole of the product. So they wanted it to be per mole of the product rather than it being like 2 moles of the product and having this be a 5 and that be a 4. They wanted to know how much heat's being given off for every 1 mole of this. So here's the important part of this. This number, that much heat's being given off for every 1 mole of that is produced. That much heat's being given off for every 2 moles of vanadium that reacts. So if this was 4 moles of vanadium reacting, we'd have double that much heat. If this was 3 moles of that being made, we'd have triple that much heat. If this was a half a mole of that being made, this would be half as much. It's also per 2.5 or 5 halves moles of oxygen. So this is related to the coefficients in the reaction. Those kilojoules per mole. And a lot of times in the AP test, it will say kilojoules per mole RXN, kilojoules per mole of reaction. So we can use this relationship in our stoichiometry and figure out how much heat is either gained or lost in a reaction. So in this case, it's telling us if only 1 gram of oxygen reacts, what is the heat change in the reaction, how much heat's being given off, assuming we have plenty of vanadium to react with that. So do normal stoichiometry, you got 1 gram of oxygen, convert that to moles, 32 grams of O2 per mole of O2. So just like we always do, we always convert to moles. We usually do our mole ratio if we're trying to get from oxygen to something else. In this case, our ratio is going to be that for every 5 halves mole of oxygen, or for every 2.5 moles of oxygen, so for every 5 half moles of oxygen that are used in this reaction, this much heat is released. There is a negative 1579.14 kilojoules of heat released per 2.5 moles of oxygen. Grams cancels, moles, we're going to be left with kilojoules. There's our answer. It's about a negative 19.74. Again, pay attention to signs a lot in this stuff. That is how much energy is released if 1 gram of oxygen is used in the reaction. Now, if we had twice that many grams of oxygen, it would be twice that many kilojoules. Do one more problem here. This time they're saying 5,000 kilojoules of energy was released. How many grams of vanadium reacted? So we're trying to get to grams of that. How many grams of this do we have to burn to make that much heat be released? So we'll start with this. We're trying to finish with grams. Start with 5,000 kilojoules, which technically would be negative because it's being released. Okay, but we can't have negative grams at the end. So I know kilojoules needs to come down here, since that is kilojoules. I'm going to say that there's this many kilojoules, 1579.14 kilojoules, are released for every 2 moles of vanadium that are reacted. So get used to using this ratio in your stoichiometry. Not too hard to do, but there we go. We can stop there if it's asking for moles. It wants to know grams. So we can say that every mole of vanadium is whatever the grams are on the periodic table. Vanadium is 51 grams per mole. And 323 grams of vanadium. So if you want 5,000 kilojoules of heat to be released in this reaction, you need to burn that many grams of vanadium with plenty of oxygen. Again, delta H is the enthalpy change in a reaction. Is there an increase or a decrease? Okay, increase in heat means it's endothermic. A decrease in heat means it's giving off heat to the surroundings exothermic.